Okay, we are now recording. Let me get from the current slide. And, all right, before we get going today, let me just go over a few things. I don't remember if you, no, you weren't here at the first of the class, so you may not have heard some of these. First, I've got a minor office hour change tomorrow. It stems from the fact that I have a doctor's appointment next Tuesday. My hematologist only sees patients on Tuesday mornings. I can't schedule on Fridays or any other time when I don't have classes, so they scheduled it for me 8:40 Tuesday morning, which means I have to be in for labs at 7:40, which means I can't be here for class at all, even if they take me at 8:40. I don't think I'll be done any sooner than 9. I doubt if I'll get out by 9, but if I got out by 9, the earliest I'd be back, or somewhere around 9:30 or 9:45, I'll lose my whole differential equations class, basically. Because the odds are I won't get back that soon, because they won't let me go that soon. So, what I talked with them Tuesday about it, and one of the students said she could stay late yesterday and tomorrow. So what I'm going to do, I did an extra hour class on yesterday, and I'll do the second hour class on extra hour on tomorrow, and that way I'll make up the class I'm missing on Tuesday. What that means is my office hours for tomorrow normally are 10 to 12 and 3:30 to 5:15, but tomorrow it's going to be 11 to 12 and 3:30 to 5:15. Now, on that subject, I think earlier in the term I said quite often I'll stay later than 5:15 unless I have to go for some reason. Well, I've been kind of volunteered to do something, and they're wanting me there at 5 o'clock, and I said I can't possibly be there at 5 because I teach till 5:15, or I'm on campus till 5:15. So I'll leave here as soon after 5:15 as I can, probably for the rest of the term. Okay, so then that means I won't have that flexibility anymore. So, and except for that, I think we'll have normal classes pretty much for the rest of the term. I hope. Well, there's one more time coming up, I think in 2 weeks. And I can't remember the exact day, but I believe it's a Tuesday or a Thursday, not a Monday or Wednesday, that I will have to miss part of one class because they've got a meeting over on the Birmingham campus they say we've got to be at. So I think it's just one class I'll miss, part of that class. So except for that, I think we're pretty much set for the rest of the term. Now, as I mentioned to you before, since I'm recording this, we're in chapter 22. This is, the title is Reflection and Refraction of Light. And 22.2, that topic is reflection and refraction. Okay, so you got ideas, reflection and refraction, right? So we did reflection last time. We're picking up this time with refraction. This is 22.2.3 on page 727. Any questions before we get started on this? Okay. Now, while reflection of light was light bouncing off of the surface and coming back to you, coming toward you, refraction of light is not the bouncing of light, but the bending of light. When a ray of light traveling through a transparent medium encounters a boundary layer leading into another transparent medium, part of the ray is reflected and part of it enters the second medium. Okay? Now, obviously, okay. Now, you won't be able to tell much this way because of the way things are, but the light coming from outside is coming toward us, and when it hits the window, it bends some, but then comes back toward us. So everything looks the same. However, if you were to raise the window there, I don't know if you'll be able to tell it or not. Let me see if you can. enough long because it's really hot outside. You can't tell. There's nothing that continues that you can really tell by. Maybe if I did a little bit less. There's not much way to tell. There is bending of the light. You just can't. The window of the glass is so thin and the leaves are not regular, so it's really hard to tell. So it's that bending of the light. The part of the light is reflected and part enters the second medium. The ray that enters the second medium is bent at the boundary. Excuse me. Got hiccups. That bending of light is called refraction. Okay? And that's what we're talking about in this section, subsection. Okay? The incident ray, the same definition we had before. The ray coming in, of course, you remember your normal line? Perpendicular to the surface? That's still a normal line. And part of this ray is reflected. Okay? But part is also bent. Okay? Now that bending is different from reflection. Okay? Now you're talking about the normal line that goes into the thing. So if this is air up here, glass down here, part of that light is bent and the incident ray is the part coming in. Okay? Reflected ray is the one coming out. Angle of incidence is equal angle of reflection. Always. Still true. Okay? The reflected ray, the refracted ray, the normal, and everything, incident ray, all those are in the same plane. Now, sorry. The angle of refraction, which is again to the normal line from the refracted ray, is theta 2. I'm so sorry. I don't know what's gotten in. Okay, that angle of refraction, theta 2, depends on the property of the medium. Okay? Sorry. The ray, all the rays in the normal line lie in the same plane. Incident, reflected, refracted, and the normal lines. All of those are in the same plane. And the refracted ray is bent toward the the refracted ray is bent toward the normal because, sorry, I've got hiccups and I can't quit. Because the velocity in the second medium, glass, is slower than the velocity in the first medium, air. You often hear let's talk about the speed of light. Sorry. And we talk about that as if it's constant. It is as long as you're in a vacuum. Air is not a vacuum. And the speed of light is reduced ever so slightly between being a vacuum and coming to the Earth in our atmosphere. Going through glass, it still goes awfully fast, but not as fast through glass as it does in air. So that's why every time it enters a second medium, it gets bent because of those changes of velocity. Okay? And it's not a major change, it's not huge, but it is a change. All right. Here is an actual picture. This is a laser ray of light. And what a laser is all the light is going in sync. I mean, it's a very defined ray. It doesn't spread very much at all. And here is the incident ray, 1, coming in. Okay? There is a little bit of this light that is reflected. You see, number 2 is much dimmer. Okay? And if I were to complete the picture for you, this is actually a picture. This is not somebody's drawing. This is actually a picture. And let's see. Actually, I think I'll leave it right where it is. Okay. Here is the normal line. Okay? This is theta I, and this is theta R for reflected. Now, so sorry. Now, ray number 3 is the ray that goes into the lucite, which is a transparent material. I'm pretty sure it's a manufactured, man-made material. And here's the normal for that, the internal normal, also an N. But you see the refracted ray, and they usually call this theta 2, and they maybe call that theta 1, if you're dealing with refraction. Because the speed of light in air, v sub a, I'm going to call it, is greater than the speed of light v sub L, which is in lucite. And that bends the ray toward the normal line, okay, theta sub 2. Now, what happens next is this third ray, this refracted ray that comes down here. Now you see also something else is happening. See how the ray is being diffused a little bit. And that's because this light in this lucite tends to bounce around a little bit more. And so therefore it gets interfered with by the molecules of lucite, so it gets a little fuzzy looking. Okay? What happens here, and we haven't gotten here yet, this place, you have a air down here or something else down here. I don't know what it is, they don't tell you. But the light can't go through it. So it gets reflected off the base of the lucite. Now what they say here is internally reflected in the lucite. So here we'll have another normal line, the normal line of the boundary between the lucite and whatever is below the lucite. So now this angle, which is the same as theta 2, it becomes, in a sense, your incident ray. I'll call it I2, and that's equal to theta R2 that's reflected from there. Now, it goes back to the surface, and here you have another normal above and below. Now, this time you're going from a slow medium, V2, VL is slower than VA, so now the refracted ray is larger than the incident ray. So sorry. Okay? So this angle, I'm going to call it theta, let's call it theta 2, why not? And, or maybe theta 4, because that's the fourth one, is less than theta 5. Well, I'll keep the numbers the same as that. So ray 5 is refracted as it enters the air from the lucite. And because it's going in a medium that slower speed of light to a faster speed of light, that means it's refracted away from the normal light. Theta 5 is greater than theta 4. Does that kind of make sense? Okay. Anytime there's a reflection, the angles are equal, incident and reflected. Anytime it's refracted, the angle in the faster medium is greater than the angle in the slower medium. Okay. And that, by the way, is the top of page 728. That same picture. I'm so sorry about the hiccups. Okay. Now, there is a quick quiz just about the middle of page 728. I think it's referring to the figure in 22.7, which is fairly close to the figure we have here. Okay? In fact, the first part is identical to this, or pretty close to it, except you don't have a reflected ray. Okay? Okay, it says if beam 1 is the incoming beam in 22.6b. Oh, 22.6b. That's this one. I thought we were, well, where is it? Oh, this one, okay. Okay, that's our figure here. If beam 1 is the incoming beam in figure 22.6b, which is this one, there's your beam 1, which of the other 4 beams are due to reflection? Okay, and which are due to refraction? So, beam 1 is the incoming incident beam. Which of the following of the others are reflected beams and which are refracted beams? 2, 3, 4, and 5. Which of those are reflected and which are refracted?
I'm not sure.
I'm sorry?
I'm not sure.
Okay. Beam 2 is reflected because it reflects off the surface here. Angle, this is equal angle of reflection. That's a reflected beam. Beam 4 is reflected because beam 3 was coming in, it reflects off the bottom of the surface, and that makes beam 4 a reflected beam. That would mean beam 3 is refracted, that means it's bent toward the normal, and beam 5 is refracted, bending away from the normal. See, this is its incident, and that's its refraction. So 2 and 4 are reflected, and 3 and 5 are refracted. 2 and 4 are reflected, 3 and 5 are refracted. This is 22. Beams 2 and 4 are reflected, 3 and 5 refracted. Got it. I'm sorry about the hiccups. Okay. That then leads us to more about refraction. Okay. Here is the formula that's called, basically, well, it relates those two. Remember, we initially said the refraction occurs because the speed of light changes as it goes from one medium to another. Okay? It's bent toward the normal if the speed goes down, away from the normal as the speed goes up. The angle of refraction then depends on the material, that's one thing, and the angle of incidence, the second thing. Now, in this one, we no longer call I for incident, because this is refraction, we call it theta 1 and theta 2, theta 1 being incident and theta 2 being refracted. So sine is not just the angle, it's the sine of angle theta 1. The ratio of the sine of theta 1 to the sine of theta 2 is inversely, ratios inversely proportional to velocities, v1, v2 to v1, okay? And that ratio is a constant, so, goodness, ratios. The ratios are inversely proportional, so the sine of theta 1 to the ratio of the sine of theta 1 to the ratio of sine of theta 2 is equal to the ratio of v2 to v1, inversely proportional. And it is still a constant. The path of light through the refracting surface is irreversible. No, I'm sorry, is reversible. The path of light through the refracting surface is reversible. They don't really do a good job of explaining what they mean there. And by the way, we mentioned Huygens before. Sorry, these hiccups. And we mentioned him that Huygens showed that wave theory of light also could explain the laws of reflection and refraction. Okay? Sorry. In section 22.7, then we'll derive those laws, but not yet. Okay. Now they say experiment shows. They don't say what experiment. Experiment shows that the path of a light ray through a refracting surface is reversible. For example, the ray in figure 22.6a, which we don't have it here. Let's show it here. That one, 22.6a. Well, it doesn't say a lot. It says travels from point A, there's point A, but the reflected ray would be in the glass, okay? Oh, from point A to point B, down in the glass, if the ray originated at B, it would follow the same path to reach the point A, but is reflected, the reflected ray would be in the glass. Okay, that's what they mean by reversible. I was trying to figure out what they meant. In other words, they have this being the incident ray and this being refracted because the velocity is slower in the glass than it is in the air. It bends toward this. But if you had light shining through the glass to go to the interface between the glass and the air, then if the arrow pointed this way, then your ray would be identical going to A, but you wouldn't have any reflection this way. The reflection that would be back into the glass. Okay? So that's what they meant by reversible. That if you shone the light in the other direction, it would follow the same path as it did coming in. The path of the light through the refracting surface is reversible. If you shone it and had what we had as the refracted ray being the instant ray, it would follow the same path and be refracted to what used to be the instant ray would be your refracted ray. That's what they meant. Now, more details. Light may move from a material where the speed is high to the material where it's lower. Okay, that's what we've been talking about. Okay? The angle of refraction, then, is less than the angle of incidence. The ray bends toward the normal when the velocity, we've already said this, when the light beam moves from the air, which is a high velocity, to glass, which is a lower velocity, still high, but lower, the path is bent toward the normal, and we've been talking about that. So, as we said before, this ratio of the sine of this angle to the ratio to the sine of this angle is then proportional to, or equal to actually, the ratio of the, because the sine of that angle is greater than the sine of this angle, so therefore it seems like there should be V1 over V2. Well, hello, hello. We've doubled the class size. And we got the top of the alphabet and the bottom of the alphabet, but all the middle of the alphabet is not here. Okay? Nope. For the life of me, yes, they've got this wrong. I've been trying to justify or rationalize it. They got it wrong. If you look in the book, this should be, let me get my pen activated. This should be theta 2, theta 1. I was going to say there's no way those ratio like that. They got that one wrong. So go back. It's not an inverse proportionality at all. It's a direct proportionality. And if you had sine of theta 1 on top and sine of theta 2 on the bottom, that would be equal to V1 over V2. But if you put it the same way the book did, it's V2 over V1. Okay. Sorry about that. I kept looking at it saying, it just can't be that way. All right. Now, that's, when we were going over that, I said it just can't be. Okay. Now, light may move. This is, by the way, we're on, I've got hiccups, so I'm sorry about that. We're right at the end of, on page 728, right at the end of 22.2.3, which is refraction of light, right before we get to the law of refraction. We're getting close to it, but not there. So, light may move from a material where the speed is low to a material where the speed is high. For instance, it may be incident in the glass with a small angle of incident, but then when it moves to air, which has a higher velocity, its angle is greater. Okay? So V2 is greater than V1, so theta 2 is greater than theta 1. More specifically, it's the ratio of the sines of those two, but then also they go as the angles themselves. So the angle of refraction is greater than the angle of incident, in this case, when it goes from a low velocity medium to a high velocity. The ray bends away from the normal then because of the higher velocity of the second medium. Okay. So when the beam moves from glass with a low velocity to air, which is a higher velocity, the path is bent away from the normal. Then here is Megan. Okay. Oh. I've got hiccups, so sorry about that. All right. We just finished 22.2.3, which was refraction of light, and are moving now to 22.3, which in our text is called the law of refraction. And that all depends on the index of refraction. Now, I've got so much drainage now. I don't know what's going on with the hiccups. Sorry. When light passes from one medium to another, it is refracted because the speed of light is different in the two mediums. So, we've said that about 3 or 4 different ways. Now, the index of refraction, N, of a medium can be defined, and here's how we define it. The triple equal sign there means this is the definition of it. The index of refraction is the speed of the light in a vacuum, that C, the constant C, the ratio of that to the speed of light in whatever medium that is, and that's your D. In most media, this difference is not very great. But the speed of light in the vacuum is always greater than the speed of light in any medium. So therefore, the N for the medium is always going to be greater than 1. Always greater than 1. And the farther it is from 1, in other words, 1.4 would be much more bending than 1.1. Okay? So, there is your basic formula for the index of refraction. Okay? Now, the index of refraction is a dimensionless number. It has no units. Speed of light is meters per second squared. Meters per second. Usually. The speed of light in the medium is meters per second. So the ratio of those have no units. The units cancel out. And N is indeed just an index, a pure number. Okay, sorry. Now, some values for N. In a vacuum, the speed of light is 1. All right, you look back at this. Speed of light in a vacuum is C. Speed of light in a vacuum would be C. C over C is 1. So the index of refraction in the vacuum, N is 1. For all other media, this is what I was saying before, it's always greater than 1. You cannot find a medium that light travels faster than it does in a vacuum. It doesn't happen. As we said, N is a unitless, in other words, a dimensionless ratio. And as the value of N increases, the speed of the wave decreases. Now, they keep using waves and rays interchangeably, and it's fine, it's okay. But we're dealing with ray optics here, typically not wave optics. And usually they make a distinction, but they're using the terms interchangeably. Okay? Now, when light is traveling through a medium, air on the outside, glass at the windows, air on the inside, okay? The speed of light changes. Faster on the outside, slower in the glass, faster on the inside, okay? But the frequency does not change. As light travels from one medium to another, its frequency does not change. Both the wave speed and the wavelength change, but not the wave frequency. The wave fronts do not pile up, nor are they created nor destroyed at the boundary. So F, the frequency, has to stay the same. Okay? And this is sort of an illustration of this. Here's the wave coming down, and notice they have the wave front at what I would consider the minimum here. And there's another one here, 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 another one. Okay? Now, the wavelength is the distance between consecutive wave fronts. Here, the wavelength in the density in the medium of higher refraction, okay, greater velocity, then these wavelengths are going to be greater. When you get the slower velocity, the wavelengths decrease because they can't go as fast. Okay? but the frequency does not change. Frequency, which is cycles per second, okay, that doesn't change. Okay. In this medium, medium 1, the index of refraction will be C over V1. Now here in medium 2, where the velocity is less, your N2 is C over V2. And when you decrease its denominator, you increase the index. Okay? Now, the frequency stays the same as the wave travels from one medium to another. They've said it like 3 times now. Remember, velocity is frequency times wavelength. Velocity is typically meters per second, frequency is per second, and wavelength is meters. So that, sure enough, meters per second is meters per second. If velocity is decreasing, that means the wavelength is decreasing, but frequency remains the same. The ratio of the indices of refraction of the two media can be expressed as various ratios. Okay? The first of these as we noted before, the index of refraction is the ratio of the one medium to another. The subscript on numerator and denominator are the same here. So index of refraction for 1 would be V1 to V2. So the ratio of N2 to N1 would be the ratio of V1 to V2. Okay? But because frequency is the same, the ratio of velocities is the same as the ratio of wavelengths. Okay? And velocity, like we said, was velocity in medium 1 is, they turn this around a little bit. What we said was N1 is the ratio of speed of light in a vacuum to the speed of light in the medium. So you reverse those two and say velocity V1 is C to N1, V2 would be C to N2, and the C's cancel out, this flips over, and that's the ratio of N2 to N1. So another way of referring to that is doing your cross multiplication. Lambda 1 N1 is equal to lambda 2 N2. So there's another way of expressing that. I'm sorry, I can't hear. Well, it's going to be a while before a break. So you want that, the last chapter test, or something else?
Did you do 5 and 6?
We've gone through 6 now. What do you need? 5 and 6? You've already done 4?
Did you do 4 last week? If you did 4 last week, I think you done. Can't recall.
What's that?
Can't recall. I might have done 4, but if it was last week, I didn't.
Okay. I'll tell you that you have turned in test 4.
Okay.
Okay. So you need 5 and 6.
Yes, sir.
Okay.
Caution in this class, very prepared, but
What's that?
I should have had you for both.
Five and 6. There's test 5. And there's test 6.
Teaching us in the fall, in the evening, maybe.
What's that?
Teaching us in the fall, in the evening, maybe.
Usually in the fall, Dr. Bryant teaches this,
Okay.
and the 202 will be in more of the afternoon, and the 201 in the
go to UA and then, but I live down here. So.
Yeah, okay. Yeah. But the 202 will be in the afternoon and 201 in the evening in the fall. Yeah. Okay. Surely. So you can write it as ratios or you can write it as products. Writing it as products, you do lambda 1, you do cross multiplication, lambda 1 n1 is equal to lambda 2 n2. So there's another way to express the law of refraction, okay, or index of refraction, okay. Here are some of the common indices of refraction. The singular is index, I-N-D-E-X. The plural is I-N-D-I-C-E-S, indices. Okay. For various substances measured with light, a vacuum wavelength being lambda 0 being 589 nanometers. I'm sorry, millimeters. Goodness gracious, what do they have there? That has to be, what is MN? I think that's supposed to be nanometers, not millinano. I've never seen that unit before. That has to be nanometers, 589 nanometers. It's wrong in the book, it's wrong on here too. That has to be nanometers. I can't think of anything else it could be. There is no unit that is in, so it has to be nanometers. Little n. So, let's look at a few. The surprising thing is they don't list a vacuum. A vacuum is exactly 1.00000, I mean exactly 1. Exactly 1. Air is awfully close to 1. 1.000293. So the 4 significant digits is 1.002. Carbon dioxide, which is a little bit greater than air in general, 1.0045. So it's still 4 significant digits, is 1.0. But then let's go up in those. That's where I like to go. Now this isn't listing everything, just some of them. Okay? Water is 1.333. Okay? Ethyl alcohol, almost the same, 1.361. Okay? Carbon tetrachloride, 1.461. Wait, I skipped one. Here's fluoride. That's calcium fluoride. Okay? That's 1.434. Okay? Then we hit fused quartz, silicon dioxide, 1.45. Whoops, I skipped another one here. Ice, which is close to water, actually less than water, 1.309. Okay? Because remember, ice is a little less dense than water. So that's 1.309. Then water at 1.333. Then your ethyl alcohol at 1.361. Then fluoride at 1.434. Fused quartz, silicon dioxide, is 1.458. Carbon tetrachloride, 1.461. Polystyrene, 1.49. Crown glass, 1.52. I'm sorry. Benzene, 1.501. Crown glass, 1.52. Sodium chloride, salt crystals, NaCl, 1.544. Then carbon disulfide is 1.628. Flint glass, whatever that is 1.66. And then I guess it jumps up to zircon. What is zircon? Cubic zirconium. I think that's the short name for zircon is the short name for cubic zirconium. 1.923, pretty high, but then the highest of all that we have listed here anyway is diamond, 2.419. That's why cubic zirconium can sometimes be mistaken for diamond, because it has almost as good of index of refraction, but then in reality it isn't nearly as good, but it's the next closest thing to it. Diamond, though, has the largest of most naturally occurring materials, and that's what gives diamonds their sparkle, because the rays really get bent in diamonds, coming and going. Okay? So there are a few of those. That's precisely the table that's in your book, table 22.1. Okay? Now, here's Snell's law of refraction. Okay? We did it in terms of velocities. Now we're doing it in terms of indices of refraction. Now, in terms of velocities, the ratio of sine of theta 1 to sine of theta 2 is equal velocity 1 to velocity 2. But when you do the index of refractions, which if it's a smaller index, that means a higher velocity. So now we have an inverse relationship, and the theta 1 is usually your index of the angle of incidence, and theta 2 is the angle of refraction. So N1 sine theta 1 is equal to N2 sine theta 2. So it's the products you put the same subscripts with. With velocities, it's the ratio you put the same subscripts in the same order. The experimental discovery of the relationship is usually credited to Willebrod, I don't know how you pronounce that, Snell, which I'm guessing was pretty much a German name unless it's one of the other Germanic languages, 1591 to 1626. That was way back in the early colonial days of the U.S. Georgia, I don't think had even been founded. I think there were 1733 or something like that. So this is way back, the very earliest of, in fact, very earliest days of colonization, the English colonization of America. Let's see if they have anything else on Snell. I don't see it. In fact, I don't even see Snell's. There it is. Okay. So I think we're ready for another quick quiz. Okay. 22.3. A material has an index of refraction that increases continuously from top to bottom. Okay, a material has an index of refraction that increases continuously from top to bottom. Now, do any of you have books? You do not. Let me try to draw this for you. Okay? Okay? Here's an angle of incident ray, and then we have a ray going like that. Okay? Here we have an incident ray, and then we have a ray going like that. And then we have an incident ray, and the ray is going like this. Okay? Now, the material has an index of refraction that increases continuously from top to bottom. It keeps getting greater, okay? Of the three paths shown in this figure, or my representation of that figure, which path will a light ray follow as it passes through the material? So it has an index of refraction that's increasing from top to bottom. Will it bend further away from the normal? Will it bend toward the normal, closer to the normal, or will it just have a constant angle? Which do you think? Which do you think? Which do you think? Okay? You have a material, this block here, its index of refraction increases from top to bottom. Okay? Is that going to bend the ray more away from the normal, more toward the normal, or just a constant angle of refraction? Okay? Away from the normal, that's what happens when you have an incident that is decreasing from top to bottom. Okay? So it would be B. B. It goes more toward the normal as you go down. Okay? Because the greater the index, the greater the bending toward the normal. Okay? Not away from the normal. Okay. Quick quiz 22.4. Thank you. Quick quiz 22.4. As light travels from a vacuum, where n is equal to 1, into a medium such as glass, where n is greater than 1, which of the following properties remains the same? The wavelength of the light, the wave speed of the light, or the frequency of the light? The which? Now, the wavelength actually decreases. Speed decreases, velocity decreases. So it would have to be the frequency, the C. That would be the same. And that, if we go back a couple slides, they said it here again and again and again. The frequency stays the same as the wavelength travels from one medium to another. On the previous slide, the frequency must stay the same. As light travels from one medium to another, the frequency does not change. Over there it says that the wave travels from medium one, the frequency remains constant. So they said it about 4 times on 2 slides. Okay, so the frequency doesn't change, but the wavelength and the wave speed do change. If I could find this. Oh, I'm in the wrong section. Yes, 4 was C, the frequency. Okay. Now, there's example 22.2, angle of refraction from glass. Example 22.3, light infused quartz. And example 22.4, refraction of laser light in a digital video disc DVD, which is basically how computers read DVDs, by light refraction. Do you want to see any of those examples done? What's that? Yeah. Okay. All right. So let's look at dispersion then. Section 22.4 is dispersion and prisms. So let's take a look at first dispersion. The angle of refraction in anything except a vacuum depends on the wavelength of the light. Okay, now do you get that? The angle of refraction in anything except a vacuum depends on the wavelength of the light. So in a vacuum, the index of refraction is 1, no matter what the wavelength is. Okay? In any other materials, the index of refraction changes slightly with the wavelength. This dependence of n on theta is called dispersion. Now, what's an example of that? An example of dispersion. The index of refraction varying with the wavelength of the light. Can anyone think of something you see, maybe not super regularly, but you've probably seen several times in your lifetime that illustrates that dispersion? The index of refraction in anything other than a vacuum depends on the wavelength of the light. Ever see a rainbow? That's an example of dispersion. This dependence is called dispersion. Snell's law indicates that the angle of refraction made when the light enters a material depends on the wavelength of the light. Snell's law basically infers that. Let's go back and see where that comes from. When you start dealing with this, the wavelength depends on that. Well, that doesn't really show it well. I don't see Snell's law listed here. I know it is. Okay. Snell's laws indicate that right. Okay. So here's variation in of index of refraction with the wavelength. All right. Index of refraction for a material usually decreases with increasing wavelength. So the index of refraction decreases as the wavelength increases. That means that longer wavelengths would have a lower index of refraction. I almost feel like that is wrong. Let's see. Here's your n, 1.4648505254. Okay? So you've got increasing indices of refraction, okay, going up. As your wavelength is increasing, which is going from violet, which is the shortest wavelength, to red, which is the longest wavelength of the visible light spectrum, then the index of refraction does decrease. Usually decreases as you go to higher, larger and larger wavelengths. Violet light refracts more than red light when passing from air into a material. So the violet light refracts more, the red light refracts less. Okay? I would guess the other way, but obviously it's this way. That's what they said, and that's what the graph shows. Now, we didn't have acrylic in the table before, but it was somewhere between crown glass and fused glass toward the lower end of the indices of refraction. Okay? Now, if you had a prism, the amount of the ray is bent away from its original direction is called the angle of deviation. Okay? Now, and the angle of deviation is called sigma. That's a lowercase sigma, not capital sigma, but lowercase sigma. Since all the colors have different angles of deviation, they will spread out into a spectrum. Violet light deviates the most, red deviates the least. Okay? So if you have white light coming in your incident ray, here you have your normal line, because you're going from a medium with low index of refraction to one with high index of refraction. The light is bent toward the normal line. Red is bent less toward the normal than what blue is, or violet is. Okay? So you have a different sigma, which is your angle of deviation for red, than you do a lesser one than you do for blue. So that's why red bends less and blue bends more. Because remember, your angle of your normal line is perpendicular to the surface, and red bends slightly toward it, blue bends a lot. Okay. Now, they introduce about middle way down page 733 a prism spectrometer. What do we mean by that? A prism, of course, is a angle type glass or other kind of material through which light bends, usually kind of in the form of a triangle. Okay. A prism spectrometer uses a prism to cause the wavelengths to separate. When they do separate, then you study the wavelengths emitted by the light source. The instrument is commonly used to study the wavelengths emitted from the light source. Now, I don't know if y'all have ever noticed this or not. Different fluorescent tubes or complex fluorescent units, bulbs, I guess it varies the material that's inside, or the phosphorescent material or something like that. And some of them will be a very bright light, some of them will be a yellowy kind of light, some of them almost a bluish kind of light. Okay? I think you see sort of the same thing with some of your LED lights, but that's a different issue. But you can look at any of those lights, look at the spectra, and see that they do differ from normal white light. Some of the fluorescents and I think LEDs come really close to it. Almost all of your incandescent lights were always a lot more yellowy than real light, than natural light. Now, some bulbs used to coat the glass a bluish color to try to get closer to the natural light, but in my mind, they always got way too blue. Okay, so what you do is you have the light source, whatever it happens to be, and it goes through a slit, so it's all pretty much parallel. That goes through a prism. The prism spreads it, disperses it, and you study the spreading of the wavelengths. Now, I guess you could call that a telescope. I would almost call it more of a microscope, but I guess it's all right to call it a telescope. Think of telescopes as being much bigger, but I guess technically that is a telescope too. So we use spectra to identify different gases. For instance, we also identify different temperatures as well. But if you have a star out there that is emitting a blue light, the odds are there are different gases in that star than there would be in our sun, which emits a yellow light. Okay? So there's also changes of temperature there, but that also probably reflects the difference of gases as well. So all hot, low-pressure gases emit their own characteristic spectra. whatever the gas that's in that tube, it will emit its own spectra, pretty much. If you were to heat up sulfur to a gas, it emits its spectra. If you heat up anything, it emits its own spectrum. The particular wavelengths emitted by a gas serve as a fingerprint of that gas. So you can, if you know that and know the field pretty well, you can just look at a spectra and tell what gas was in that. Now, sometimes if there's a huge mixture of gases, it's hard to pick out all of them, but you can usually pick out the dominant. Some of the uses for spectral analysis: identification of molecules. So I was talking mostly about elements to begin with. Identification of elements in way distant stars, and identification of minerals. Okay, you can do all that using spectral analysis. Okay, and thinking of another example of that, but I'm not sure it's all that good or directly related, so we'll just leave that alone. And as I mentioned, rainbows. Okay? Now, by the way, there's a tip here on dispersion. Light, a shorter wavelength such as violet refraction. Okay, we already said that. There's a pretty good picture illustrated in 22.15 and another in 22.16. Then there's Applying Physics 22.3 on dispersion, and you can sometimes explains what you see going through a thickness of glass or water or something else like that. Example 22.5 is light through a prism, and then 22.5 is the rainbow. Now, I mentioned this already. Here it's talked about in greater detail. Now, what happens with a rainbow? The reason a rainbow happens, when does a rainbow happen? After it rains. So what must be true after it rains? You have a lot of water droplets in the air. Very high humidity, and you have little bitty droplets of water. Now, we are going to assume those droplets are very close to spherical. They probably aren't exactly spherical, but they're close. So we have rays of light that's going through the air, of course, but they also go through these droplets of water. So that ray of light strikes a drop of water in the atmosphere, because after rain you have lots of droplets out there. It undergoes both reflection and refraction. We're basically a little more interested in the refraction, though there's another type of reflection we're going to talk about too. But the first refraction is at the front of the drop. So here we have a raindrop, right? Incident light comes in to the raindrop and gets bent away or toward the normal. Incident light hits a raindrop. Does the light get bent away from or toward the normal? That's toward, because the index of refraction is greater in the raindrop than it is in air. Okay? Not a lot of difference, like 1.33 compared to 1, but it is some difference. Now, which gets bent the most, violet or red? Violet, for sure, because the shorter wavelength gets bent the most. Okay? So violet gets deviated the most, red light deviated the least, but it still gets deviated. So we get a spreading there. Now that's when it comes into the droplet of water. At the back surface, the light is reflected again. Now what that is called is total internal reflection. I've kept thinking all chapter long, they're finally going to define that, but they're not. They're going to wait till next chapter, I guess, to define it, or later in this chapter somewhere. So the back surface of light is reflected. Now, catch this. Here's the light coming in. It's bent, red is bent slightly toward the normal, and violet is bent more toward the normal. But then you have reflection. So the angle of incidence, equal angle of reflection here, but they're at different locations on the curve, so your normal lines are at different locations. So they get bent at different rates, and therefore they cross and flip before they exit. But then when they exit the light, the rain droplet, the water droplet, do the refracted rays get bent toward or away from the normal then? Do they get bent toward or away from the normal? Do they get bent away from it, because you're going from low velocity to high velocity, or higher index of refraction to lower index of refraction, so you get bent away from the normal line, okay? And which gets bent more? Yeah. Again, the violet does, okay? It gets bent differently coming out. But because of that flipping in here, the violet now winds up on top and the red on the bottom. Okay. Now that's when the light is coming in the top. If you went in the other way, it just reverses itself. Okay. So it's refracted again. The rays leave the drop at various angles. The angle between the white ray light and the violet light is 40 degrees, and the angle between the white light and the red light is 42 degrees. Okay? Because violet gets bent more here, gets differently there, flips, and then gets bent more, that one gets bent less, so violet accentuates that change, and that's 40 degrees there, whereas the red is 42 degrees. Violet light refracts through larger angles than the red light does. Okay. But it's coming in and going out, the refraction is back away from it. Okay. Now, if the raindrop high in the sky is observed, the red is seen. Okay? High in the sky, you see the red because it's bent at 42 degrees, the violet only at 40 degrees. So further up here, you get red on the higher part, violet on the inner part. Okay? And that's your rainbow. Okay? A drop lower in the sky would direct the violet light to the observer. So you see what you're doing, you're looking at light coming through different drops. It's not all the same drop, it's different drops. You're standing here, and the violet coming off this one, you miss. You see the red off that one. The violet coming off this one, you see, and the red you miss. And all the ones in between would be those, the orange and the yellow and the green and the blue and the indigo before you get back to violet again. Okay? Now, what do you notice about this picture? Yeah, there's a second rainbow. And that's at a further out, further up, greater angle. Well, what do you notice about that rainbow? The second. It's not as clear, it's not as bright. One other thing. Colors are reversed, exactly. Now, what can cause that? Okay? Well, it's hitting, okay, we'll see several things. Whoa, goodness gracious. They do not describe the double refraction. Shame on them. Let me try to give it to you. Let's go back to this, okay? When the incident ray just barely nicks this, and again, the red doesn't get bent as much, but the violet gets bent some, but then you have a large angle here, then it gets down here before it leaves and gets bent again at a large angle, okay? Now, what happens there is you get a crossing when it gets reflected once, but then you get a crossing a second time, so violet lines up on, you see them in different order, so your violet lines up on top rather than the red, because you have double internal reflection, and each time it flips at another time. So, indeed, that's what causes the second one. Why is it not as bright? Because not as much light is caught by the raindrop. See, this is a fairly good amount of light that goes through here. Only a little bit of light is going to get caught there, so it's not nearly as bright, and it's a double reflection, internal reflection, so it flips again, and that's why it flips the other. So that describes, I'm surprised they didn't do it. My physical science book does a better job than that. Now, the next topic here is on Huygens principle. This is 22.6. Here is a picture, a portrait, or something of Christian Huygens. Pretty sure he was Danish, right? They don't say here, do they? Seems like he's Danish. I always get Denmark and the Dutch. The names are somewhat familiar, and I sometimes get them crossed up. But I think he's Danish. Christian Huygens. And look again at his lifespan, 1629 to 1695. And again, this was early in our colonization, English colonization of America. He is best known for his contributions to the field of optics and dynamics. Okay? He deduced the laws of reflection and refraction, and he explained double refraction. So he was quite a bright mind and dealt largely with light and stuff, though he did do some in dynamics as well. Okay? So here is Huygens' principle. Huygens assumed that light is a form of wave motion rather than a stream of particles. Remember, who was it at first suggested the particles? Who was the first scientist to suggest particles? Actually, way ahead of his time, Isaac Newton. Okay? I'm pretty sure he didn't understand particles the way we do today, but he suggested it. But then Huygens and these other guys came along and suggested waves. Okay? Huygens' principle is a geometric construction for determining the position of a new wave at some point based on the knowledge of the wavefront that preceded it. Blah, blah, blah. So what do we mean by that? All points on a given wavefront are taken as point sources for the production of spherical secondary waves called wavelets, which propagate forward in the forward direction with speeds characteristic of waves in the medium. And if you're going from a high velocity to low velocity, that would be from a low index of refraction to a high index of refraction. After some time has elapsed, the new position of the wavefront is the surface tangent to the wavelets. Okay? Now again, the wavelets and that kind of stuff, they're not particularly clear yet. But let's take a look at it. At t equals 0, the wavefront is on the plane A prime. And for the life of me, I do not see A prime anywhere in this figure. The points are representative sources of the wavelets. I'm almost certain they've got the wrong slide picture there to go with this slide because you don't see any wavelets. After wavelets that have moved some distance c delta t, which is a distance, speed of light times the time interval, that would be a distance, a new plane, B prime, can be drawn tangent to the wavefront. And frankly, that looks like it's the wrong figure. Okay? I think if you look on page 737, figure 2221, that's what it's talking about. Okay? Really poor the way they have kind of messed up the slideshow here. Okay? Huygens construction for a spherical wave, the inner arc represents part of the spherical wave, the points are represented points where the wavelets are propagated, and the new wavefront is tangent to each point on the wavelength. Okay, again, the previous slide, this slide was 22.21a, and this one should be 22.21b. Okay? Let's see if they show this anywhere else. No, they don't. Now, let's consider Huygens' principle applied to reflection and refraction. Okay? The law of reflection can be derived from Huygens' principle. And again, I don't see an A prime here. It's in the text. They've just got the wrong figure. That's a figure we had way, way earlier. That was 22.2a. Has nothing really much to do with what we're talking about here. What you need to be looking at is 20. Look at this. No, yeah. I see what happened now. They were supposed to use figure 22.22. They used 22.2. So evidently someone was sloppy in their writing or sloppy in the reading. This should be 22.22a, not 22.2a. Okay? So you almost have to turn to your book to see this. Okay? Yeah. Okay. The reflected ray wavefront is CD, which we have there. Again, you have to have your book to see it really. Okay? Now, this was 22.2b, not 22.22b. So they got it all messed up again. Sorry. But on 22.22b, there is a triangle ADC, and there is is congruent to the triangle AA prime C. Those are equal triangles, congruent triangles. Your theta 1 is equal to theta 1 prime, and that basically was your law of reflection. If the angle equals the reflected angle, that's your law of reflection. So you have to look at 22.22b, not 22.2b. Or not. Okay, let's see if they get the next one right. No, they botched these up so badly. That was the figure we had, 22.3. It's supposed to be 22.23. So they messed this one up too. Sorry about that. But if you get your books, you'll see it. It's Huygens construction for proving the law of refraction. Okay. So basically you have to get your book. They just mess this up. So at time delta t, ray 1 moves from A to B. And just to tell you what was happening there, A to B is in the medium, the higher index of refraction medium. It takes a while longer before ray 2 moves from A prime to C because it's got a longer journey to go at that angle to reach the glass. So that's the difference there, A prime to C. Now, from the triangles A prime, C, which you can see there in your text, and ACB, which you also see in there in your text, that's the time that it takes between the parallel parts of the wavefront. At A, it's already starting to bend. At B, it still is in air for a while before it reaches the place where it's going to bend. So that's your difference there. And you match up the values for those that you do have, relating the angles and the indices of refraction and that type of thing, and that's where you get the law of refraction. N1 sine theta 1 is equal to N2 sine theta 2. All right, now finally we reach total internal reflection. Okay? Total internal reflection can occur when light attempts to move from a medium of higher index of refraction to one of a lower index. And ray 5 shows that here. Okay? Now, let's start with ray 1. Ray 1 is going along the normal line, so there's no refraction at all. You're going along the normal line, the angle of incidence is 0, angle of refraction is 0. No refraction. When you go to angle 2, you get some bending away, going from index of the higher index of refraction to lower. You get some bending away. Then it's hard to swallow. Okay? Some bending away. Here's your angle of incidence, theta 1. Because this has a higher index of refraction than up here was a lower one. This has been away from, theta 2 is greater than theta 1. So you have a bending away from the normal one. But a little bit of this actually reflects, and the angle of incidence here, theta 1, is equal to angle of reflection there, would also be theta 1. Okay? Now, you go further out here, and they did draw another normal line, but now this angle of incident is a lot larger, so your bending's a lot larger, so the angle of ray 3 actually gets bent quite a ways. Okay? Well, go on down for a greater angle of incidence here. And now, at this point, some of the ray, none of it escapes because the part that would have escaped before now skims the surface. Okay? Finally, when you get to 5, and by the way, that angle where it skims the surface is called the critical angle. And then anything past that critical angle, you get total internal reflection. Nothing is bent. You can't. Your angle is so great here that when you use the refraction law, it goes beyond horizontal. Okay? So you get total internal reflection. You got a little bit of reflection before, it gets greater and greater and greater until suddenly it's all reflected. Every bit of it. Okay? Does that make sense? All right, so the critical angle, a particular angle, let me find this in the book. Oh, I don't see it in the book. I know it's here, but, oh, there it is. It's still on page 738. I was looking at 739. Okay. The critical angle, a particular angle of incidence, will result in an angle of refraction of exactly 90 degrees. That's what we get here. Here's your angle of incidence coming from the high index of refraction to a low index. That's where you always have to. You get bent away from the normal line. And if this is a great enough theta c here, then your what would have been your refracted ray skims the surface. That would be ray 4, and that would be total, the angle theta c here is your critical angle. Anything beyond that, you get total internal reflection. Okay? This angle of incidence is called the critical angle, and here's what's true about it. Sine of theta c is equal to n2 over n1. Okay? Now this is a small number because n1 is greater than n2. Okay? So n1 is greater than n2. And that critical angle that makes your angle of refraction 90, and the sine of 90 would be 1, that would be your critical angle of incidence. What you're missing there is sine of the refracted angle, and that would be 90 degrees. So sine of 90 is 1. So just leave off the 1. Okay, does that make sense? Now, as you're coming closer and closer to this, okay, when you're here, a lot of the thing is refracted, okay? Some is reflected, but not too much. The greater you go, the larger percentage gets reflected, and the lesser percentage gets refracted. When you reach the critical angle, anything past that is total reflection. So you really get a much better reflection then. Of course, this is always true when the incident index of refraction is greater than the exit angle of refraction. Okay. Now, continuing with critical angles, for angles of incidence greater than the critical angle, the beam is entirely reflected at the boundary. That ray obeys the law of reflection at the boundary, where angle of incidence equal angle of reflection. Total internal reflection occurs only when light is incident on the boundary of the medium having the lower index of refraction than the medium in which it is traveling. Okay? Let me read that again. When light is incident on the boundary of a medium having a lower index of refraction than the medium in which it's traveling. So if the incident medium is larger index of refraction, you can have total internal reflection. And that's the only time you can. Now, that leads to yet another, and by the way, there's applying physics 22.4, total internal reflection and dispersion. And then there's example 22.6, a view from a fish's eye, which the fish are always in the medium of high angle of refraction, of index of refraction, to a lower one when they're looking out at the sky. So now we'll do 2.7.1, which is dealing with fiber optics. Are you familiar at all with fiber optics? Okay. What you'll hear sometime, let's see, we started at 5:30 and go to 6:20, so we haven't gotten there yet. So, see, okay. What fiber optics is receiving a lot of attention now, because broadband, good quality internet signals, they're talking about cities running fiber optics so they have better, faster, more reliable internet signals. Okay? And if and when they do that, everybody will have really good internet. They're already doing it for other things, such as do you know what an endoscopy is?
Is that a surgery?
Huh?
Is that a surgery?
Not a surgery. It's an invasive thing, but what they usually do, and it can be anywhere, usually they go down your throat and look at, say, your stomach, esophageal lining, your stomach lining, possibly even into the small intestine. Anytime they're looking at there, they've got a device going down there, it's bending, twisting and stuff. They send light down and then they get a signal back. That's fiber optics, okay? Anything that will do this, and they're really, really high quality generally. An application of internal reflection, because there's nothing lost due to refraction, it's all reflective. The plastic or glass rods are used to pipe light from one place to another, okay? Now, you can't have a real sharp bend in it, because if you do, you may have refraction. But as long as the bends are gentle, then the light suffers internal reflection, internal reflection, internal reflection, internal reflection, internal reflection, and light travels at very close to the speed of light. Okay, you gotta go. You're probably not coming back. Well, it's up to you, but I'm going to keep teaching, so you can go on if you want to. It'll be out there on YouTube.
Okay. Can I have my test in lab?
Pardon me?
My test in lab, what are you
Yes, she was good.
Yeah.
And did you get back 3 and 4?
No, he's still waiting on the
I've been, this other woman actually paid for the course, but she's never been here.
Okay.
And they haven't removed her yet, as far as I know, so I can't do anything till I find out. This was the test on 5.
Is it supposed to be 6?
Huh?
Is it supposed
Oh,
to
have you already turned in the 5?
be? Yeah.
No, I don't. That's the only one
at
I've
the
got.
top it says file. So it's-
Oh, wait, I'm sorry, that's 201. I
Oh.
picked up the wrong one. Yeah, that's 201.
It's 2 pages.
I was in 201. I haven't gotten to 202. Okay. Let's see. Yeah, you turn in test 5.
Okay, 4. Test 5 said 4, right? And I scratched it out in this
Right.
spot.
Yeah, all of you go see the whole test basically.
So y'all got 6 Monday.
It says test 5 at the top.
Okay. You weren't here for the electromagnetism lab, right?
Is that what y'all do Monday?
That's the one we did Monday.
Yeah.
Okay. You actually get a stapled copy. I think if you listen to the YouTube video, you can pick up most of it.
Okay.
I forgot to carry my computer for one part, but you can check one of the others and probably get that too. Okay? And then here's test 5 that she said that's a 2-pager.
Okay. So.
That's actually test 6.
Okay. So you didn't turn that 3, 4, or 5 because
I can't because I've got to find out what they're going to do. Yeah.
Okay,
Right.
you have mine. Okay.
Okay.
So that's turned in Wednesday.
Yeah. Right. And yeah, it's graded, and I think the grades are out on Blackboard too. I'm not sure, but I think they are. Okay, so fiber optics, the plastic or glass rods are used to pipe the light from one place to another through total internal reflection. They use this all the time. Applications include medical use for fiber optic cables for diagnosis and correction of medical problems. Like I said, endoscopies, I'm pretty sure that's what they use for colonoscopies, just about anything that they're actually looking at inside of you. I'm pretty sure they do them for various types of exams where they're looking for things like, I believe, bladder cancers and stuff. They'll use something on the outside too, something like ultrasound and things like this. But quite often, if you're wanting to get more detail, they'll actually run a fiber optic up some orifice to get that. They also use them for telecommunications. That's what I'm saying is the highest quality signals that you can get, I think, from anything or from your fiber optic cables and things like that. I'm trying to remember if some of these sub-oceanic cables might also be fiber optic. I can't say for sure if they are. It seems like I've read or heard that may be the case. But that's what fiber optics is. Let's see if there's another slide. That is the end of topic 22. And as I said to the people who were here earlier, we don't have a lab for this topic. What we're going to do is combine the labs for 22 and 23 together and form one lab on the two of them. Okay? But a good thing to look at is your summary. 22.1 has, some verbiage plus one formula. That's Planck's formula. 22.2 has a figure and law of reflection. They don't get into refraction yet. They tell you about it, but they don't do it. Then 22.3 is the law of refraction. They first give you the index of refraction. There's a formula, a figure that illustrates it, and then they give you another formula or two which relates your index of refraction to wavelengths and also to the angles of refraction of incidence and refraction. Okay? Then 22.4 and 22.5 are together, and they show dispersion and prisms and the rainbow. Those go together. There's one figure and a little bit of verbiage. Huygens principle is stated in 22.6. Total internal reflection in 22.7. Critical angle is defined, and the formula for it is given. Figure there showing it. Conceptual questions then. The odd number answers are in the back, so you can do any of the odds 1 through 15. Okay? Then the problems, these are going to be closer to what you see in your test that you'll be getting. I don't have this one quite finished yet. Knock on wood, have it ready for you Monday. The nature of light, 22.1, any odd numbers 1 through 5. 22.2 and 3, reflection, refraction, law of refraction. That'll be any of the odds 7 through 27. Then 22.4 is dispersion in prisms. That would be any of the odds 29 through 33. Total internal reflection, any of the odds 35 through 43, and then we have the additional problems which relate across the sections, and that would be 45, odds 45 through 61. All right. That would have been a very hard section to do a lab in because it's mostly definitions, okay? Not too much of stuff that you can actually sink your teeth in. So we're combining the lab for 22 and 23 together, and that's where we go next. Goodness gracious, I keep hitting the wrong button there. I need to go back rather than cancel out. Okay, so here we go again. Here we go. 23, mirrors and lenses. And this time they do them in the same order. Okay, PowerPoint lectures. Okay, it's 7:24, and we go, technically at 7:20, I would have called roll, and lab goes from 7:30 to 9. So, doesn't look like we're going to have anyone here for the lab period. So, here we go, slideshow, current slide. Chapter or topic 23, mirrors and lenses. Now, some of the verbiage here, or this is, I guess, just an introduction here for mirrors and lenses. The development of mirrors and lenses aided the progress of science in many ways, led to microscopes and telescopes. Microscopes study very tiny things that are very, very close. Telescopes study typically very large things that are very, very, very far away. It allowed the study of objects from microbes and telescopes to distant planets, more like distant stars with telescopes, even as far as distant galaxies, a few galaxies. Images can be formed by reflection from mirrors, and images are formed by refraction through lenses. So you see this chapter very directly follows the previous chapter, and that's why I'm just combining the labs to go together, because anything we did reflection, and refraction in the previous topic, we're going to do again in this one, so we're just going to do one big lab of this one. We'll look at the formation of these images, and we'll continue to use the ray approximation. You can also do it with the wave approximation, but it's a lot more convoluted. The rays, if you follow the rules, they go pretty handily. Okay? So a little bit on the notation for mirrors and image. Mirrors and lenses. The object distance is how far the object that you're looking at, either going to reflect through the mirror or refract through the lens. The distance from the object to the mirror or lens, that's the object distance. Now they denote that by a P. Okay? And I'm not sure why. Okay? I would prefer, because it makes so much more sense to me, to call that D sub O, distance of the object. Okay? So whereas they're going to call P, I'm going to call it, if you don't mind, it just makes everything, to me, make a lot more sense, D sub O. Okay? Meaning distance of object. Okay? The image distance is the distance from the image to the mirror or lens. The images are formed at a point, the point where the rays either actually intersect or appear to originate. Okay? If it's an actual intersection where the rays really do form, okay, then you have a real image. If it's where they look like they came from, that's a virtual image. That's denoted by Q in the text. I'm going to call that DI. Again, why P and Q? Why not DO for distance of object, DI for distance of image? It just makes more sense. Okay? The lateral magnification of the mirror or lens is the ratio of the image height to the object height. Now there they've given you a couple of other things. So since we have a distance, let's also have a height of the object and a height of the image. We're going to be measuring those things as well, okay? And the ratio of the image height to object height is the magnification, which is capital M, which is height of image to height of object. If the image is larger than the object, you've magnified it. If the height of the image is smaller than the height of the object, it's actually a demagnification, or it's not really a negative magnification, but it's just the magnification is a fractional number rather than a number greater than 1. Okay? So I'm introducing a few other symbols and notations than what the book uses. It just makes more sense. Okay? Now, I've already suggested something here. There are two types of images. Images are classified either as real or virtual. A real image is formed, or real images are formed, at the point where the rays of light actually do intersect. And real images can be displayed on screens. Actual real images. On films, on things like that, those are real images. Now, a virtual image, on the other hand, virtual images are formed at the point where the rays of light appear to be coming from, but really aren't coming from there. The light appears to diverge from that point, and the virtual images cannot be displayed on screens or on a film or somewhere else. They're just virtual images. They're not really there, okay? It just looks like they are coming from there. Okay. Now, let me go back that one slide. Let me show you what the book uses. They use as the height of the object to be H. This is the book. This is mine. And this is the book. They use H, and for height of the image, they use H prime. And again, why not go on? So this would be the same in the book as H prime over H. Why not go on and use a subscript and make it clear? Clear, clear, clear. I do not see the reason not to, but they don't. Okay. Now, here's a quick quiz. Okay? And I wish somebody were here and had a book, but I don't think anyone does. Okay? I mean, nobody's here, so I don't know if you have a book. In fact, since someone's here, I'll turn off the projector. There's no reason voice involved for my benefit, because I've got a screen to look at, and I'm going to flip the lights so I can read better. Since I'm not looking at the screen, the light will be weakening the image of the screen, diluting it, polluting it maybe. All right. Now, the quick quiz 23.1. It shows an overhead view of figure 23.3. The image of a stone as seen by an observer 1 is at C. Okay? Now, what we've got here I believe they're talking about mirrors. Okay? They've got to be talking about mirrors. Okay? So, here we have one person looking this way, and this is person number 2. And we have another person here looking this way. This is person number 1. here we have the mirror. It's supposed to be a plane mirror. No, let's not make it there. You scoot it up just a little bit. Okay? Because we have an object here. It's a rock. Okay? And then we have a mirror here. For person 1, the image of this rock is right there in the mirror, but the image is behind the mirror. The rock is in front of the mirror, but he's looking at an image behind the mirror. Okay? Now, so that's at C. So that's what it says here. In the overhead view of figure 23.3, the image of the stone as seen by observer 1 is at C. And this would place C. Okay? Over here is A. Over here is B. Over here is D. And over here is E. All right. It says, where does observer 2 see the image of that rock? There's only one rock. Here it is. Okay, that rock. Where does observer 2 see the image of that rock? Okay? Now, observer 1 sees it as C because the angle of incidence is equal to the angle of reflection, and it just coming right back, it looks like it's coming from there. Now, person 2, the image from the rock is coming here and bouncing off the mirror and going that way. It appears that the rock is there. It really isn't. The image is a virtual image, but it appears it's there because, let me see, is that right? No, I don't think so. Yeah. The image is being reflected off there, so the object's here, the person seeing the rock there, but it makes it think the rock's there because it looks like the light rays are coming from the rock back there. Okay, I believe that's right. Let me check and see. This is topic 23. Topic 23. Yeah. Whoa. 23.1. Can't be. They've got it wrong. Person 1 sees it at C. Person 2 can't be looking at it and thinking it's at C too. So they got that one wrong. Sorry about that. The image is not C, it's B. Sorry about that. They messed it up. Okay. Now, there is a little tip here, and this goes back to the previous slide, no, 2 previous slides, when they're talking about magnification. You think in everyday terms, magnification means something is magnified, made to look bigger. That's not what we're talking about here. Magnification is not the same as enlargement. Magnification, if it's a positive number, is an enlargement. If it's a negative, sorry, I said that wrong. If it's a number greater than 1, it is an enlargement. If it's between 0 and 1, it's actually a reduction, but it's still a magnification. Okay. There is a neat little example here, example 23.1, mirror, mirror on the wall. It gives you an idea of what size mirror you can see your whole body in. And basically, the clue here it's about half your height. It has to be placed correctly, but still half your height will show your full image, which seems a little bizarre, but it's really not. I mean, it really is true. If you were here, I'd ask if you want me to do that one, but since you're not here, and every time I've asked, you said, no, we've got them in the book, so I won't do that. All right. Oh, okay, here's magnification. Again, and this book calls it lateral magnification. It's defined as the image height to the object height, which is exactly what we had back here. The lateral magnification of the mirror or lens is the ratio of image height to object height, and here's where they actually give it. In my notation, I like to call this h sub I over h sub O. Why not go on and make it clear? Rather than having to remember, is the prime the height, the image, or the object, is the h the image or the object? Do a subscript so you know it's the object or the image. Now, and as the note said, the lateral magnification doesn't always mean enlargement. The image could be smaller than the object, then the magnification would be something less than 1. Okay? I think I'm going to pause for just a minute. I'm so sick and tired of hiccuping. I hate to break now, but I'm going to... All right, sorry about that, but I've been struggling with hiccups all class long, and I finally got so tired of them, I said I've got to go drink some water slowly and try to break the hiccups. And so far, knock on wood, I think I have. Okay, so we hit that magnification, remembering it doesn't mean enlargement. It could be that the image is actually smaller, and we'll see examples of that. So let's look at a flat mirror. And your flat mirror, this figure in your text is on page 751, figure 23.2. Okay, just about exactly here. Okay. All right. The properties of the image can be determined by geometry. Okay. And we're going to use a few rules to do this. Okay. Now, the object is here, the gray arrow upward. They just draw an arrow. I've seen some people use candles, but arrows are really easy to draw. Okay. Even I can draw an arrow. Okay, poorly, but I can. One ray starts at P, so here's the object here. Its height I would call h sub O for height of the object. This, what they call P, I would call distance of the object. Okay. Now, we're going to draw our rays from the point, the top of the arrow. And one of these we're going to draw perpendicular to the mirror, going to Q, and then it's reflected back directly at you because it's a flat mirror. But it looks like that's coming from the dotted line here, and this Q is what I call the distance of the image. Okay? But you only have one line there. You need a second one. So a real easy one to do is draw a second ray leaving from the P, hitting the, and by the way, later we'll have a name for this, but the place where the, oh boy, that horizontal line there is sometimes called the axis of the mirror, but of course this being a flat mirror, it doesn't have an axis, but we'll I like to use that term because we'll use it later. Axis of the system, okay? And it goes and hits the base there, and it's reflected this way, okay? Well, currently you're not going to see it, but it looks like it's coming from the dotted line back there, and sure enough, they meet at P prime. And P prime is, because of your equal angles and everything else, basically P prime is the same distance from the back of the mirror as P is from the front of the mirror, so your Q, your distance of the image, is the same as distance of the object. Now this I would call the height of the image. They call it H prime, I call it HI, so that I don't have to remember what the prime stands for. And you'll notice that's exactly, or it looks like it's exactly the same height as the object. So the magnification of this mirror would be 1, okay? Now, the second issue here is what kind of image is it? There is no place that those rays are actually combining from or to. They look like they're coming from P prime, since they look like they are, but the image can't really be back there. It looks like where it is. This makes it a virtual image. Now, it looks like there's too many loops there, but it's virtual image. Now, let me give you another hint here. This will be true in mirrors. It will be true in lenses. If it's an upright image, I can't think of a single instance that that's not going to be a virtual image. If it's an inverted image, then those are just about always, I think always, real images. Okay? Now, with a mirror, the virtual images are always going to be behind the mirror because you can't see through a mirror. You can't see the image back there, but it's where the image looks like it is. For a mirror, any real image, if you ever have a real image, it's going to be in front of the mirror because that's actually where the rays are going to cross. As you see, all the rays hit the mirror and bounce back, so they stay on the same side of the mirror as the object, but the image seems like it's on the back side. That's what makes it a virtual image as well. Okay? Then when we get to lenses, we'll see just about everything is reversed from that. But not everything, but a lot of things are. So, one ray starts at P, follows the path PQ, reflects straight back on itself. The second ray follows the path to PR, reflects according to the law of reflection, but you're not down there to see it, so dot your line back there where it looks like that reflected line is coming from, and you see it looks like they're originating or coming from point P. P prime. So that's your image. It's a virtual image. It's an upright image, and it's a magnification of 1. Okay. Now, I was playing around with the idea of this. See, another part of me wondered if the light going through here, the ray goes this way. I'm sorry. The ray leaves here, hits the mirror, and yeah, what you see is here, but it seems to be back there. I think that's still correct. Okay. think we got it right. Okay. Now, the image is as far behind the mirror as the object is in front, so therefore P is equal to, and they're using absolute value, which is a safe way to do it, absolute value of Q. Now what I would call that is DO is equal to, and you can put absolute value as you want to, DI. Now, the reason for absolute value is there are times when we say that anything in front of the mirror or the lens is a positive quantity and behind it is a negative quantity, but we're not dealing with the signs here. The image is unmagnified, meaning it's neither enlarged or reduced, so the image height is the same as the object height, so, and I would have called that H sub I is equal to H sub O, and the magnification then would be 1. Okay, so it's exactly the same. Now, the image is virtual because it appears to be coming behind the mirror, but there's no rays that ever go behind the mirror. They can't, okay? The image is upright, and you'll usually find that those, when it's virtual, it is upright. When it's upright, it is virtual. That means it has the same orientation as the object, and that's why looking in a plane mirror, you see your image, because it's there. There is an apparent left to right reversal of the image, okay? And you'll notice that when you look at your face in a mirror, plain mirror, you probably do it every morning, maybe some evenings, you look at a mirror, maybe every time you go to the restroom if there's a mirror there, you look in the thing. And if you take your right hand and wave, the image looks like it's the left hand, not a right hand, okay? So that's what they mean. There's apparent left-right reversal of the image, okay? Now, there's an application here of day and night settings on auto mirrors, okay? Now, this figure, yeah, it's at the top of page 752, okay? When you're setting your mirror in the daytime, your incident ray that's coming from whatever's behind you that you're looking at comes in and hits the mirror, and notice that you have a thickness of the mirror that's changing, okay? And what's happening is the incident ray comes in and hits the eye. Then you have a little bit of diffraction going back and hitting the back of the mirror, which is where the silver is, the reflecting side, and that's almost close to incident, 90 degrees, right, almost on the normal, but not quite. It's reflected angle of incidence, equal angle of reflection, so it goes right back out almost as tight as it came in, and then it goes back to the interface between the glass in front of the reflecting side and the air, and when it hits there, it's refracted away from the normal line because the index of refraction of air is less than that of the glass, and so you see it at B, but what was coming in was parallel to you, but you're seeing there. Okay. Now at night, you wouldn't want that because you would get basically so what you're seeing is the reflection off the back of the mirror, okay, which is what you expect, okay? But in the night setting, if you got the reflection off the back of the mirror and that was a bright light coming in, it'll almost blind you, make you lose your night vision, okay? So what you do, whereas at this angle, you have the reflection off the surface of the glass. Before it went in and got refracted, you have a reflection with heading off in that direction, which you don't use or see. It's not as good of an image, so we'd rather have the day image, the one off the back of the mirror. But at night, we don't want that one off the back of the mirror because it's too bright on you. So then you get just the reflection off the surface, that interface reflection, and that's what you see, whereas the actual light from the cars behind you and stuff, they'll be sent off at B, which is not going to bother your night vision. So in the daytime setting, the bright beam of reflected light is reflected into the driver's eye. In the nighttime setting, the dimmer beam of the reflected light is directed to the driver's eyes, while the bright beam goes elsewhere. So yeah, you see some of the light from the car, but it's not nearly as bright. But you see, you got your pupils are open, you're receiving more light in than you really need to handle. So yeah, you can get by with the dimmer light because your pupils are open wider. Okay, that's an application that was shown on the top of 752. All right, then we go to another type of mirror, and these are spherical mirrors, okay? Now, there is an Applying Physics 23.1, which is shown here. I've seen it in other renditions. Really what you've got here is, you don't see it, but the guy's leg is behind the box there. What you're seeing is his leg in front and the image of his leg behind, making it look like he has both legs off the ground and is just sort of floating there. It helps him that he has his hand stretched out, make it look like he is floating. But that's an illusionist trick, okay? I can't remember if we have a mirror here that you could do that. We used to, but I think that mirror's been taken down. So if I can find one, we may look at that in the lab. I don't think we'll see it. So here's spherical mirrors. And these are mirrors in the shape of a segment of a sphere. You don't ever have a whole sphere. Usually you don't. And there are two types of spherical mirrors. The concave spherical mirror, which has a silvered surface of the mirror on the inner or concave side of the curve, okay? The convex spherical mirror has the silvered surface of the mirror on the outside of the convex side of the curve. And when we see a picture of this, I'll point that out a little bit more. This is a concave mirror. Now, I can remember one of the earliest physics classes I can remember taking, and my teacher saying, think of this as the mouth of a cave. It sets back into the rock, so that's a concave mirror. And I've liked that ever since. It helps me remember that. Now, every mirror, if it's a circular mirror, a spherical mirror, has a radius of curvature, r, okay? And that would be from the center of the mirror, that's what the C stands for, and your r is the radius of curvature, and we call this the principal axis, and that's why I wanted to call that before, the axis, okay? And then the V back there, it's not real clear what that is, okay? But that's the center of the spherical segment that goes from the center of the mirror through the center of the curvature, through the center of the mirror, and going back. That line makes the axis of curvature, and V is the back part of that, is the center of the spherical segment, okay? The line drawn from C to V is called the principal axis of the mirror, okay? So that's the nomenclature that we're going to use there. Has a radius of curvature R, center of curvature located C, always in front of that silvered surface, okay? The point PV is in line with C and with the center of the mirror and is the center of the spherical segment, okay? And I guess that means it's this right here. So when they say that, the spherical segment, that would be this as being the V. And the line from C to V then is the principal axis of the mirror, okay? Now, on the other hand, this is the B part of that same figure. If you have a point source of light and you place it somewhere, okay? Let's say O, with O being the outside of the center of curvature, okay? Further from the mirror than the center of curvature. That means that the O, that's the object, that's the source of the light, the object. The rays are drawn from O, okay? Now, since that is just a point source, you can still draw, well, actually, you can draw 3 rays. They only show 2, okay? They show one incident ray going down below the axis, and let me give you a hint here. Your radius of curvature to any point is your normal line, always. Radius of curvature here, that's your normal line, okay? That is your normal line. And always the angle of incidence equal angle of reflection. So it's going up here, angle of incidence this time is here, and angle of reflection is there. They come back, and your image, or the place where those rays converge, and they actually do converge there, that's where your image is. That makes it a real image because the rays actually cross there. If your object is outside the center, your inner image is going to be between the center and the mirror, okay? We'll talk about something else later, okay? So hang on to that, okay? So the point source of light is placed at the O, object. The rays are drawn from O, the object. After reflecting from the mirror, the rays converge at a point I, the image, and the light actually passes through that point, so the image is real, okay? If the rays diverge from O at small angles, they all reflect through the same image point I. Now, enough said about that. Okay. Now, rays are generally assumed to make small angles with the mirror, okay? When the rays make a large angle, then you have converging at different points other than the image point. The results may be a blurred image, and that effect is called a spherical aberration, meaning not reality, okay? So your small angles, like this angle and that angle, okay, those make small angles here. So these, there again, they don't show the center of this mirror, but here's your normal line, and that would be angle of incidence, angle of reflection. For this one, another small angle, angle of, yuck, this is a really ugly line, angle of incidence, angle of reflection. That would be your actual image, okay? But when you make the rays too far away, too great of an angle, then again your angle of incidence equal angle of reflection, angle of incidence equal angle of reflection. Now these are coming in here, and that gives you a distortion. Now they've really exaggerated this, but that gives you your spherical aberration. You don't get a clean, sharp focus. You get a blurred image, okay? So you usually try to keep your angles fairly small, okay, for spherical mirrors. Now the other thing they did here, they made a very tight circular mirror, so it's real easy to get with the object where it was a a large angle and still hit the mirror. Okay. Now, I'm trying to remember. Nah, it was something different. I was going to say the Hubble Space Telescope, when they first put it up, they had an error in the calculation, and they had to go up and do some adjusting of that in order to get clear images. I was going to say they had spherical aberration, and it may have been, but you see, Hubble Space Telescope isn't a spherical mirror. It's a parabolic mirror, so that's why my illustration wasn't quite accurate. Okay, so it wouldn't have been a spherical aberration, it would have been another aberration. Now, let's actually have an object there, not your just a point source. Okay, point source, we know what it is. Now here's the object. Now they're leaving one piece out here, and it's okay, they can get by without it. But I wish they had put it in, and I'm going to show it to you. Okay? Again, this is the height of the object, and this will be what I call the height of the image. Notice it's inverted. That means it's going to be a real image. Shouldn't be saying that yet. But here's your principal axis, and you draw two rays from the image here, from the object here. One goes straight to the center of the mirror, and there's your V. That's where it should have been on the other one. And it's reflected back in equal thing in this direction. Okay? The second one, you go to the center of the mirror, and because it's to the center of the mirror, its angle, the normal line is right there. See, on when you go to the V of the mirror, the vertex, you might say, of the mirror, that then makes your principal axis your normal line, and so your theta, this is theta incident, this is theta reflection, then your, but if you go to the center, then it's on the radius, so it comes back directly, okay? And where those two cross, there is your real image. The rays actually cross there. It's a real image. And the object is way out here, well past the center, and that makes the image, it's real, so it's inverted, but it's also, the magnification is less than 1. Okay, and we'll talk about that in a minute too. Here again, they say the distance of the object, so why not call it d sub O? Here's the distance of the image, why not call that d sub I? The radius is your radius of curvature, is that, whether it's from C to V or from C to the mirror here or anywhere on the mirror, that's your center to the curvature. Now, they've left out an important point, okay? I'm going to show you that important point. Exactly halfway between the center and the mirror is a point, and this is called the focal point, F. Usually little f, okay? Now, here's two things about the focal point. Number one, any ray, incident ray that comes in parallel to the axis, and I can't draw a parallel line to save me, parallel to the axis, it's going to be reflected through the focal line because the center is your normal then, okay? What's more, any ray that goes through the focal point here is going to be reflected parallel. And that also crosses here. So all of those lines cross there, every one of them, okay? Now they simplified things by just having two lines, but you could have up to two more, okay? So it makes it simple just to have two, and it's easier to do usually. It only is going to cross at one, especially since you're drawing on freehand. That makes it a little easier. But there is another issue there that you could deal with. And they haven't talked about focal point yet, which I'm sort of surprised, okay? So that gives it. So anytime that image is inverted, it's going to be a real image. Anytime the image for a mirror is actually on the same side of the mirror of the object, that's where the rays actually are, that's going to be a real image, okay? When the image looks like it's behind the mirror, that's when it's a virtual image, and every one of those is going to be upright, otherwise the same orientation of the object, okay? But on the other hand, your magnification, if your object is outside the center of the mirror, you are generally, for a curved concave mirror, you're going to have the image is going to be smaller. The height of the image, the absolute value of that, is going to be less than the height of the object, meaning magnification is less than 1. All right. Now, they come up with one other thing, which is fine. The magnification we already knew was the height of the image to the height of the object. They use h prime over h. I just assume do image to object, okay? Now, by similar triangles, which they haven't really shown here, but it is true that this is also a ratio of the distance of the image to distance of the object, okay? Oh, minus, okay? Now, that minus sign can be a pain in the neck, okay? For mirrors, of course, the P has to be a positive number on the same side of the mirror as the silvering, otherwise you can't see anything. But the Q, if it's on the same side for a mirror, since that's where your image should be, it's positive in front of the mirror. So this would be, but the height, the image is inverted, so that would be a negative height, so you would have negative over positive. The object is standing upright, so that would be a positive. So technically that magnification, that's why they usually say the absolute value of this, but if you're not doing that, that actually would be a negative, meaning it's an inverted image, but it's also shrunk in a real image. So if you're using the distance of image and distance of object, that's why you have to put the minus sign in front, because if it is real, then that needs to be, the height of the image is always going to be inverted, so it's going to be negative. Okay. Now, they're talking about some angles here. And I can't figure the figure in the text. I was afraid of that. Oh, got it. The angle they're talking about here, alpha, is this angle, not these angles here. Angle of incidence, angle of reflection. Okay? These are your alphas, and they're opposite angles from each other, so they are equal to each other. Okay, now, that said, let's take a look at some of the things, and they do have this in the book. The tangent of alpha. Looking at this angle right here, the tangent of alpha is opposite over adjacent. Okay, that's the tangent. What is the adjacent there? It's the distance from the object to the center of the mirror. Okay? Okay? Well, the center of the mirror is what they call the P, I call distance of object, minus the r, the radius of the mirror, okay, because the distance there. So this distance here, that distance right there, is the distance of object, or what they call P, minus the radius of the mirror, which is the distance from the center to the vertex of the mirror. So that's going to be, so the tangent of theta is equal to HO over DO minus R. And that's what they have here. Now, if you go the inside angle theta, alpha, which is this, I'm sorry, I put theta down here because I'm used to using theta. It's alpha. Call alpha. Okay. Okay. Tangent of alpha is that. That's from your thing here. Let's also look at this angle alpha here. And the tangent of alpha here is your height of the image, which they call H prime. That's your opposite side over your adjacent side, which is the difference in R and Q over capital R minus distance of image. Okay? And that's how they get those two formulas. Okay? Except they have a minus here. Now, why the minus? Because the H prime is negative. Okay? It's pointing downward. The other distances are, you can call them positive. So that's why it's called negative. Okay? Now, why do they even mention those or bring them up? Not entirely clear yet. Except that maybe, let's look at the ratio of height of image to height of object. That's your magnification. So magnification is height of image to height of object, which would be the ratio of di minus r times tan alpha over d0 minus r tan alpha. Okay, that's HO. Well, the tan alphas obviously go away, and they have another formula here. Now they left the minus sign in there. I took it out and changed the order of it. They have another thing here that I don't see. Oh, I'm sorry. Yeah. Since this was also equal to, down here, di over do with a minus sign, I thought that's what they were trying to get to. They say simple algebra reduces this. Okay? Now, what is that simple algebra? I need more room so you can see what I'm intending to do here. So what I think I'm going to do is erase a bunch. In fact, maybe erase everything. Hopefully I won't need something later. But let's do that. And what we were left with, I'm going to write it the way they did. R minus di over p minus d, no, this is do minus r, okay, is equal to q di over do. Okay, let me see if I can clean that up a little bit. Okay. All right. Now they say simple algebra shows that. I'm not absolutely sure this algebra is that simple, but let's see if we can follow it. Let's make this r over do minus r minus di over do minus r. Okay? That doesn't help any. I think I erased the wrong thing up here. This is di over do. Okay. I don't see the simple algebra. I'll take the word for it. I know it's true, okay? But, I'm sorry. This equation here, then, okay, sorry, I was looking at the wrong thing. Let me go back. This equation reduces to something else, okay? And here's what they're saying it does reduce to, okay? Let's try this. Multiply these two together. do times r minus di is equal to di times do minus r. Okay? So this is dor minus dodi is equal to dido minus r, di. Okay? These two are the same, so let's add this to both sides. Okay, and while we're at it, let's add r di to both sides. Okay, this goes away, that goes away. Okay, so what do we have now? R times do plus di is equal to 2 di do. Okay? Now, divide both sides by r. Okay? And by di do. These go out here, this goes out there, and this becomes do over di do plus di over di do is equal to 2 over r. Okay? Here the DOs go out, here the DIs go out, and this 1 over distance of image plus 1 over distance of the object is equal to 2 over the radius. Okay? Now, that expression is called the mirror equation. Let's see if we can find that. There it is. That is called the mirror equation. Okay? Geometry shows that relationship between the image and the object distances is that. Now, I really want to do this. As I said before, that point that's halfway between the center and the vertex, I called it the focal point. Okay, I called it F. And that would be R over 2, half of the radius. Okay, halfway, midpoint between the vertex and focal. That's it. So this would be 1 over F. That is how I remember the mirror equation. Not 2 over R, but 1 over F, where F is the focal point. Same thing, but it is there. And, oh, and they get to it the very next slide. Okay? If an object is very, 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 very far away, then P is considered to be, or DO is considered to be infinity, and 1 over DO, 1 over infinity, would be 0. So you have 1 over DI would be 2 over R. So basically the incoming rays are essentially parallel, like you see here, and all those rays hit toward the focal point. I put, oh no, okay. The focal length is little r, the focal point is capital, focal length is little f, focal point is capital F. Points are capitals, the lengths are small letters. Okay, so that would be a focal length. And that's either the distance from the mirror vertex to the focal point, that would be your little f, or from the center to the focal point. Mostly we go mirror. Okay, that's where it's coming from. That image point is called the focal point. The distance from the mirror to the focal point is called the focal length. That focal length is exactly half of the radius of curvature. So it sits exactly midway between the center and the V. Okay? For P approaching infinity, Q approaches R over 2, which is your focal length. Sorry, I'm hiccuping again. Why? I don't know. And so we've got that covered. And yeah, that's the figure A at the bottom of page 754. Okay. Sorry, I've got the hiccups again. The focal point is dependent solely on the curvature of the mirror, not on the location of the object. The focal point is always there, and it's always R over 2. So the mirror equation now is written as what I said I like to see. 1 over P plus 1 over Q is equal to 1 over F. Okay. And they make a little point about focal point is not the same as the focus point. And they really don't describe what a focus point is either. They just assume you're talking about, the place where the light rays focus to form an image. That's, if you call that the focus point, that's not the same as the focal point. I call it the image point, okay, so that's why not even mess with that one. So, okay. Here is an actual shot, okay? Parallel laser beams coming into a spherical mirror, and sure enough, you see if they're parallel coming in, they always go through the focal point, right there, okay? Those are actual rays, okay? Reflected, 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 and if you did one right through the center, it would come right back through there as well. Okay. So let's move on to convex mirrors. And let me just say this. A convex mirror is sometimes called a diverging mirror, and that's because no matter what you do to it, the rays are diverging when they leave the mirror, which means they never form a real image, ever, okay? We just saw that concave mirrors can form real images. However, you can get a concave mirror to form a virtual image, and most of you have seen that, especially any of you with makeup mirrors. It's exactly what they are, okay? The convex mirrors, those are the kind that you usually see, sometimes we'll see on grocery store aisles hanging up near the top. So someone in the back of the store, so someone sitting in the office, which is usually elevated, can look at those mirrors and look down every aisle and see what's going on. So they can watch for shoplifting is, I think, the major reason, but also in case anyone falls or anything gets spilled or dropped or, broken or something like that, they can see it right away and get someone to clean it, or help the person, or whatever is the case. But they're diverging mirrors, and as such, the images are always smaller than the objects. Always, always, always. Because the rays are diverging, the place they would look like they're coming from, on the back side of the mirror, which would be a virtual image, of course, then they are always going to be tiny, small back there. Now, a lot of the times, the right-hand mirror on your vehicle, if you haven't noticed this already, look at it. Usually there's a little bit of small print there on the lower side of that and say, objects are always smaller than they, no. Objects appear smaller than they are, which in effect makes them seem a little further away because they're smaller. So you have to be careful for that, but the reason they make those diverging mirrors, not very much, but just a little bit, is so you can see places that would otherwise be blind spots. They give you a little bit wider angle of vision so you can do this. So the rays from any point on an object diverge from the reflection as though they were coming from some point always behind the mirror. The image is always virtual because it lies behind the mirror. They can't really come from there because you can't get rays from there. At a point where the reflected rays appear to originate. In general, the images formed by a convex mirror are always upright, and if they're upright, they're always virtual, and like I said, they're always smaller than the object. So the magnification is less than 1. Sorry about the hiccups. I hate to stop again. I'm going to try to keep working through them. No, they're getting too bad. I'm going to have to pause again. I'll be right back. I don't know. All right. Sorry about the second delay, but I just couldn't keep from hiccuping again. Sorry. So here we have the object in front of a convex mirror or diverging mirror. And let's draw our lines that we would normally draw. Now, this one they've got it more like I'm used to. Let's draw an incident ray from the object to the mirror. Okay? Now, the radius, which comes from the center to that point, that is your normal line. So here's your angle of incidence, angle of reflection, sorry. They're equal to each other on either side of the normal line. Okay? Obviously, that's going out into space somewhere. But it looks like it's coming from down here at the focal point. But remember, any rays coming parallel appear to go through the focal point, but the focal point was behind the mirror, so it would be going up here. So sure enough, that's where it's heading. A second one of these would be the one going to toward the center of the mirror, and that is the normal line, so it reflects right back off of it. It looks like it's coming from here. So these two, from the focal point from the parallel to the focal, coming from the focal point, center back, that's your point there. Now the one they did not show that they did before is a ray, well no, that I did before. If you had a ray that looked like it was going toward the focal point, then that one comes off parallel, and sure enough, parallel would be right there as well. So you get three different rays that you can use, and they all three look like they come from that place, so this would be the image back here. So I call this DI, I call this DO, distance of object, distance of image, okay? And this would be the F here, the distance from the center of the mirror to the focal point is your focal length, okay? And all of your formulas still hold. It's a virtual image because it's behind the mirror. It can't actually be coming from there, but it looks like that's where it's coming from. It's always reduced, always reduced. It's always upright because it's a virtual image, and it's so the magnification, like I said, is reduced, so it's less than 1. Anything else? I think that's all the things we talked about. Okay. So there's your image, virtual image behind a convex mirror. I'm sorry. Yeah, convex mirror. Okay. Now, sign conventions. I knew there was something else. So let's talk about them. The equations for convex mirrors are exactly the same as concave mirrors, but you need to use the sign conventions. And here's what it is. The positive sign is used where the light is. That's in front of the mirror, okay? Front side of the mirror. The negative sign is used behind the mirror, or the back side. That's where virtual images are always formed. They're always on the back side of the mirror, okay? So that means your DO, the distance object, is always positive. Always, 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 okay? Your distance of the image, they call the Q, that is negative here because the image is behind the mirror. The focal length is negative because it's behind the mirror, okay? And actually, if you did R, if you did, don't really need to, but if you did, that would be negative too because that's behind the mirror as well. Except usually we have R as positive, so don't worry about that one. Okay. So, So here's a diagram for the signs. If you're on the front or the real side of the mirror, the P is always there, by the way, so that's always positive. If the Q is on the front side of the mirror, the side to the right actually is, then you consider it positive. Instant light would be the P, reflected light, the Q. Okay, flat, convex, or concave mirrored surface is always on the side that the front side. Okay, that way you don't have to worry about any diffraction or other things through the glass before it gets to it. In reality, you know, a lot of mirrors are silvered on the back, but we're going to assume they're silvered on the front. Okay, so your back side or your virtual side, and by the way, any image on the front side of the mirror is a real image. So the back side or the virtual side, the P and the Q are negative. Now, I can imagine a P ever being negative because your object is always in front of the mirror, so it's just not happening, okay? No light is ever on the back side, okay? So basically, flat mirrors are always going to produce upright, virtual images on the back side of the mirror. Convex always are going to be the same, virtual, upright, back side of the mirror. Your concave, you can have real images inverted on the front side of the mirror, okay? But you can also have some virtual images on the back side, and hopefully we'll see one of those before we're through. We're getting close to being through, though. Okay, so here's a table of sign conventions for the mirror. That was a figure, here's that. The object location, and again, it doesn't make any sense to say if the object's in back of the mirror, you don't see it then. I mean, I don't know. It doesn't have a reflection. So I don't know why you would ever say it's in back. The object is always placed in front of the mirror, so it's always positive. The image, distance to the image, can be either in front of the mirror, then it's positive, and back of the mirror it's negative. The focal length, if it's in front of the mirror, it's positive, so that means concave mirrors, positive, convex mirrors, always negative, the focal length. The image height, if it's an upright image, it's positive. If it's an inverted image, it's negative. The object height is always considered positive. They don't put that down here. The magnification is positive if it's an upright image and negative if it's an inverted image. What the magnified part is, if it's reduced, that means your absolute value of it is between 0 and 1. If it's actually magnified, the absolute value of it is greater than 1. Now, of course, with the plane mirror, the magnification is 1. Focal length is infinity, and actually, technically, I don't care which one, positive or negative infinity. Q is always negative. Image height is positive because it's upright. Okay, those are just a few of the sign conventions. Now, the ray diagrams, we've already been showing them, but let's make them a little more formal. Ray diagram can be used to determine the position and size of an image. To get exact numbers, use the formula, the mirror equation. But to get the general idea, use the ray diagram. And if you're careful, you can come pretty close to reality. Okay, they are graphical constructions which tell the overall nature of the image. They can also be used to check the parameters calculated from the mirror and magnification equations. So how do you draw the ray diagram? To make the ray diagram, you need to know, number one, the position of the object. And frankly, I cannot imagine that ever being negative, so that's going to be positive. Okay? And number two, It's always positive, and I can't think of much else to say about it. The distance of the object is always positive, okay? The position of the center of curvature, though, a concave mirror is going to be positive, convex mirror is going to be negative. 3 rays are drawn. They start from the same position on the object, usually the point, the top, okay? Or usually the objects are upright. I was trying to think of the other thing I was going to say about the objects. I can't think of any reason to draw an object upside down to start with. Draw the object upright and then see what the image comes out being, okay? And then also draw the object on the positive side of the mirror and then see where the image comes out, okay? 3 rays are drawn. They all start from the same position on the top, on the object, usually the point of the object, if you draw the arrow. The intersection of any 2 of the rays at the point locates the image. The 3rd ray can serve as a check of the construction to make sure you're about right. So what are those 3 rays? We've done them before. Let's do them again. Ray 1 is drawn parallel to the principal axis. Parallel to the principal axis, and is reflected back through the focal point. Okay? Now, if the focal point is on the front side of the mirror, then that ray actually has to go through the focal point. Its reflection goes through the focal point. If the focal point's on the back side of the mirror, then it has to act like the reflected ray acts like it's coming from that focal point. Though, you know, this focal point behind the mirror, it never goes back there, but it acts like it's coming from back there. So that's the first, the one parallel to the principal axis. The second ray, drawn through the focal point and is reflected parallel to the principal axis. Okay? Now ray 2, again from the top of the thing, thrown through the focal point. So if it goes through the focal point and the focal point's on the front side of the mirror and the object is in front of that, then it goes through that focal point and comes out parallel to the principal axis. It's got to. Those 2 things are inverses of each other. Okay? If it comes in parallel, it goes to the focal point. If it comes through the focal point, it comes out parallel. Okay? The 3rd ray is drawn through the center of curvature, is reflected back on itself. Okay? Mirrors, that's what happens. Okay? Now, notes about the rays. The rays actually go in all directions from the object. We just pick those 3 rays because we know where they're heading. Okay? The image point obtained from the ray diagram must agree with the value of Q calculated from the mirror equation. I call it DI. They call it Q. I think we're getting close to being out of time. Here are the ray diagram examples. Note that the changes in the image as the object moves from the focal point. Okay? Now, let's start with a concave mirror. This is where we had it before. The object is way on the front side of the mirror, outside of the focal point, outside of the center of curvature, somewhere out there. Then the object is here. Your first ray goes parallel to the axis of the mirror. It has to go through the focal point and go out that way. The second ray goes through the focal point, from the top of it, through the focal point, and comes out parallel. That right there gives you the image. Inverted, reduced, and between the focal point and the center. If the object is outside the center, the image is, this is for a concave mirror, between the focal point and the center. Okay? Real, because it's inverted. Okay? They actually cross there. Let's do the 3rd line. You go through, the 3rd line goes through the center of the mirror, and therefore its reflection is right back through the center of the mirror. And sure enough, that also lands on the same point. So that's what you've got. So if you're outside the focal point of a convex mirror, you're going to have a real, inverted, reduced, image outside the center, that's what you're going to get. The one they show here is fine, except that looks like it's very close to being right on the center, okay? Because the image height certainly is, the image is inverted, making a negative height, but the magnitude looks very close to being what the other is, okay? Now, like I said, you could place the object inside the focal point. If you do that for a concave mirror, the first ray is going to go parallel to the axis and comes out through the focal point. Okay? It heads down this way. That's ray 1. Ray 2 acts like it's coming from the focal point. It can't go through it because the object's inside, so it acts like it's coming from the focal point. It goes out parallel. And if you look at those two, you see they're diverging. So this is not going to be a real image. They can't converge on the front side of the mirror. It just can't happen. So draw the extensions back for the 1 and the 2, and you have an image back there. Okay? Let's do your third ray as if it came through the center, through the object, and then bounced back off. Well, again, that's diverging from 1 and 2 on the front side, converging somewhere behind, which means it's a virtual image. It's an upright image. It's a magnified image, okay? That is your makeup mirror, okay, you ladies. I'm married to a lady, so I know about makeup mirrors now. She has one right in front of the mirror in the bathroom, okay? And that is always a virtual, upright, magnified image. Makes the pores on your nose look really, really big, okay? Now, the third location, oh, they're not doing one. I wish they had done one where you have the object in between the focal point and the center. If you had drawn that one in there, then the image is going to come out outside of the center, magnified, reduced. I wish they had shown that one, but they didn't. Okay. If you have the object right on the center, it comes out inverted, but the same size on the center as well. Okay. They didn't show those two cases, but maybe they will later. Let's look at the convex mirror, the diverging mirror, and we're basically out of time. I'll finish this one and we'll shut it down. Anywhere you put that object, the first ray goes in parallel to the axis. It acts like it's coming from the focal point, but the focal point is a negative. The focal length is negative because the focal point is behind the mirror, so it comes out as if it's there. Boy, diverging like crazy. The second one acts like it's coming from the focal length, so you draw that line from the top of the object to the focal point, and then it comes out parallel from the mirror, from where it touches the mirror, it comes out parallel. Dot that one back, and there you have a upright image again, and it's also, so it has to be virtual, but it certainly is reduced. And then draw one toward the center. Remember, the center is behind the mirror as well, so draw one from the center. It reflects just as if it was going to the center. It reflects right back off the mirror. Dot that one back, and sure enough, it also is a virtual image, upright, reduced, behind the mirror. Okay? So we'll start next time with the 3 I was just starting to talk about. Okay? All right. Actually, these are the same 3 we just saw, but they're a little bit bigger, so we'll do that one right here. Okay? Now, we've still got quite a bit of chapter to go. We've still got all of our lenses to go. And we call them thin lenses, by the way, for a reason. So we will do that. I think we might finish it. Here's what the plan is. We will do, if we can finish the chapter next time, we'll have the lab the last 2 hours. If we don't have time to finish it before those 2 hours, we'll go on and start the next chapter, which is your topic 26, which is relativity. That's the first of your what they call modern physics. And that's the last thing we're going to do if we have time to do it. And I think we'll get to it. Now, if we finish that in plenty of time, then we'll go back and try to do, no, I don't think we're going to have a chance of doing that. So we'll just leave it like that. All right, that pretty much wraps us up for now. I'll shut this down.